Welcome to Learn from the Sleeping Legend. Tonight, we follow the life and discoveries of Galileo Galilei. Relax, slow your breath, and let your mind drift as you listen. There is nothing to remember, nothing to solve. Just absorb his story, his curiosity, and his courage. Stay with us until the end, and let the lessons of observation, discovery, and wonder quietly settle in your mind. Relax and enjoy. In February 1564, a child was born in Pisa, Italy. Galileo Galilei entered a world of established certainties, of accepted knowledge, of questions that seemed already answered. From his earliest years, something distinguished him. While other children accepted what they were told, Galileo watched and wondered. He noticed small things, how objects moved, how sounds echoed, how patterns repeated in nature. His mind naturally asked why and how, when others simply accepted because. His father, Vincenzo, was a musician and mathematician. This combination shaped young Galileo's thinking. From music, he learned about harmony, rhythm, and mathematical relationships in sound. From mathematics, he learned about proportion, measurement, and logical reasoning. Both disciplines taught him that underlying patterns exist beneath surface appearances. The family expected Galileo to study medicine. At 17, he enrolled at the University of Pisa for medical training. Medicine offered respectability and steady income, practical considerations for any family. But Galileo's attention kept wandering. During lectures on anatomy and herbal remedies, his mind drifted to questions about motion, mathematics, and natural philosophy. Medical texts interested him less than questions about how the physical world actually works. According to tradition, during a church service in Pisa's cathedral, he noticed a lamp swinging on its chain. While others prayed or daydreamed, Galileo watched. He timed the swings using his pulse and observed something unexpected. Whether the lamp swung widely or narrowly, each complete swing took approximately the same amount of time. This small observation intrigued him. It suggested regular patterns existed in nature, waiting to be discovered through careful attention. The swinging lamp became, for Galileo, a question worth investigating further. He eventually left medical studies, choosing instead to pursue mathematics and natural philosophy. His family disapproved. This path offered less certain prospects, but Galileo's curiosity pulled him toward understanding how nature works, not how to treat human ailments. Picture young Galileo, in those early years, watching everyday phenomena with unusual attention, noticing patterns others missed, asking questions that seemed unnecessary to his teachers, small observations accumulating, patience developing, a method of inquiry beginning to form. Galileo developed a fundamental conviction that would guide his entire life's work. Knowledge about nature comes primarily from observing nature itself, not from consulting ancient authorities about what nature should be like. This sounds obvious now, but represented a significant shift in his time. The accepted approach was studying what Aristotle and other ancient scholars had written about nature. When questions arose, you consulted texts, not the physical world. If Aristotle said heavier objects fall faster than lighter ones, that settled the matter. Why perform experiments when authorities had already provided answers? Direct observation seemed unnecessary, even presumptuous, as though you distrusted the wisdom of the ages. Galileo thought differently. He respected ancient scholars, but recognized that nature itself holds the final authority. Books contain human opinions and reasoning. Nature contains actual facts. When these conflict, observation must take precedence over text. This wasn't disrespect for tradition. It was recognition that careful attention to the world reveals truths that pure reasoning or inherited assumptions might miss. You can think about nature all you want, but at some point you need to actually look, measure, and test. Consider how this applies beyond science. How often do we accept conventional wisdom without checking for ourselves? How many beliefs do we hold simply because they're widely repeated, not because we've examined them directly? Galileo's observational approach required patience. You can rush observation. Patterns emerge gradually through repeated attention, not in sudden flashes of insight. He would watch the same phenomenon repeatedly, under different conditions, measuring carefully, noting variations. This patience produced reliable knowledge. When Galileo made a claim about nature, it rested on dozens or hundreds of careful observations, not speculation or hope. His conclusions had solid foundation because he had done the slow work of watching and measuring. The lesson: observation before assumption, looking carefully before concluding. Patience to let patterns reveal themselves naturally, rather than forcing premature explanations. One of Galileo's most important insights was recognizing that natural phenomena follow mathematical patterns. The universe operates according to quantifiable relationships that mathematics can precisely describe. He wrote that philosophy, by which he meant natural philosophy, or what we call science, is written in the grand book of the universe. But this book cannot be understood unless you first learn the language it's written in. That language is mathematics. Its characters are triangles, circles, and other geometrical figures. What did he mean by this? Consider a swinging pendulum. You could describe it qualitatively. It moves back and forth in a regular rhythm, gradually slowing until it stops. This description captures something true, but remains imprecise. Or you could describe it mathematically. The period of swing depends on the pendulum's length and local gravity, following a specific equation. With this mathematical description, you can predict exactly how long each swing will take, allowing precise timekeeping. Mathematics provides precision impossible with words alone. It allows exact prediction, verification by others, and clear communication across languages and cultures. Mathematical relationships transcend personal interpretation. Galileo discovered mathematical patterns everywhere he looked. Objects falling near Earth's surface accelerate uniformly. Distance increases proportional to the square of elapsed time. Projectiles follow parabolic paths determined by initial velocity and gravity. Pendulums swing with periods related to their length by a specific mathematical relationship. Each discovery revealed order beneath apparent complexity. The same mathematical laws apply everywhere, in Pisa or anywhere else, to large objects or small ones, yesterday or today. This universality meant nature was fundamentally comprehensible through systematic study. The mathematical approach also enabled technology. Once you understand how something works mathematically, you can engineer applications. Understanding pendulum motion enables accurate clocks. Understanding projectile motion improves artillery and architecture. Mathematical knowledge translates into practical capability. Think about patterns in your own life. Habits, relationships, work. All contain regularities that careful attention can reveal. Sometimes stepping back to see underlying patterns, the mathematical structure beneath surface complexity, shows pathways forward that weren't visible up close. Galileo wanted to understand falling motion precisely, but objects fall too quickly to measure accurately with available timing methods. He couldn't stop motion, couldn't slow it down directly, couldn't measure distances and times with sufficient precision during a brief fall. His solution showed experimental genius. Use inclined planes. Let balls roll down ramps instead of dropping them vertically. By adjusting the ramp's angle, he could control motion's speed. Steeper ramps produced faster motion, gentler slopes, slower motion. But the essential character of accelerated motion remained. He marked the ramps with regular intervals and used water clocks for timing. Water dripped into a container at a steady rate. By weighing the collected water, he could determine elapsed time. Crude by modern standards, but sufficient for detecting patterns. Through many repeated trials, he discovered that distance traveled relates to the square of elapsed time. If a ball rolls a certain distance in 1 second, it rolls 4 times that distance in 2 seconds, 9 times in 3 seconds. This quadratic relationship characterizes uniformly accelerated motion. The inclined plane experiments also addressed a long-standing claim by Aristotle that heavier objects fall faster than lighter ones. This seemed intuitively correct. Drop a stone and a feather, and the stone reaches the ground first. But Galileo reasoned that the feather falls slowly, not because of its weight, but because air resistance affects it significantly. He rolled balls of different weights down the same ramps and timed their motion. The results were clear. Weight made no difference in the rate of acceleration. Heavier and lighter balls accelerated identically. This contradicted centuries of accepted teaching, but matched what careful observation revealed. The experimental evidence was undeniable. When you actually measure carefully, rather than relying on casual observation or inherited assumptions, reality reveals its true patterns. Picture Galileo in his workshop, rolling balls down ramps hour after hour, measuring water weights, calculating ratios, repeating trials to verify results. This painstaking work lacks drama. No sudden breakthrough, no flash of genius, just patient accumulation of careful measurements, gradually revealing mathematical relationships. This is how progress often actually happens, not through sudden inspiration, but through sustained careful work, not through clever reasoning alone, but through the patience to test ideas against reality repeatedly until patterns become clear. The story about Galileo noticing the swinging cathedral lamp captures an essential quality. His attention naturally went to physical patterns others overlooked. While most people saw only a lamp, he saw a physical system with discoverable properties worth investigating. He observed that a pendulum's period, the time for one complete swing, remains nearly constant, regardless of how wide or narrow the swing is. Whether the pendulum swings through a large arc or barely moves, it completes each oscillation in approximately the same time. This property is called isochronism. This discovery had immediate practical implications. A pendulum could serve as a reliable timekeeper, its regular rhythm providing consistent time intervals. The period depends primarily on the pendulum's length, not on the swing's amplitude or the bob's weight. While Galileo conceived of pendulum-based clocks, he never built a fully working model. Others would later implement this idea successfully, creating the first accurate mechanical timepieces. But Galileo recognized the principle and understood its significance. The pendulum also provided another example of mathematical regularity in nature. The relationship between pendulum length and period follows a specific equation involving the square root of the length. This allowed precise predictions about how any pendulum would behave. Consider what made this discovery important beyond its immediate application. Galileo found deep order in simple, everyday motion. A swinging lamp became a window into universal principles. This particular pendulum reveals truths about all pendulums everywhere. This represents a key aspect of scientific thinking, recognizing the universal in the particular. This specific observation reveals general patterns. This ball rolling down this specific ramp shows how all objects accelerate under gravity. Careful study of individual instances reveals principles that apply broadly. The pendulum's regular rhythm also offers insight beyond physics. Many natural systems have characteristic rhythms: heartbeats, breathing, seasonal cycles, tidal patterns. These rhythms reflect underlying order. Working with natural rhythms, rather than fighting them, produces smoother, more sustainable patterns. In human terms, energy levels, creativity, productivity often follow rhythmic patterns. Recognizing these rhythms and working with them, rather than imposing arbitrary schedules, can improve both well-being and effectiveness. The pendulum's lesson applies more broadly than its immediate physics. In 1609, Galileo heard reports of a Dutch invention, a tube with lenses that made distant objects appear closer. He immediately grasped the potential and set about creating his own improved version. Within months, he had built telescopes magnifying objects up to 20 or 30 times, far better than the initial Dutch designs. While others saw commercial or military applications, spotting ships from shore, surveying enemy positions, Galileo turned his telescope toward the night sky. This decision transformed astronomy and eventually human understanding of our place in the cosmos. Through his telescope, Galileo saw things no human had ever observed. Each observation challenged accepted beliefs about the heavens. The moon's surface wasn't smooth and perfect as philosophers claimed. It was rough and mountainous, with craters, peaks, and valleys casting shadows. This suggested celestial bodies were physical places similar to Earth, not fundamentally different perfect spheres. He observed dark spots on the sun, sunspots, showing that even the sun wasn't uniformly perfect and unchanging. These spots moved across the sun's surface, indicating the sun rotated. The Milky Way, which appeared as a glowing band across the night sky, resolved into countless individual stars when viewed through the telescope. The number of stars exceeded anything previously imagined. Most dramatically, he discovered 4 moons orbiting Jupiter. Night after night, he observed these moons, now called Io, Europa, Ganymede, and Callisto, changing positions relative to Jupiter. This proved that not everything in the heavens revolves around Earth. Here was clear evidence of a system with its own center. He also observed Venus, going through phases similar to the moons, sometimes appearing as a crescent, sometimes nearly full. This observation made sense if Venus orbits the Sun, passing between Earth and Sun at certain points, moving behind the Sun at others. The Earth-centered model struggled to explain these phases. Each observation provided evidence supporting the heliocentric model, the idea that Earth and other planets orbit the Sun, proposed decades earlier by Nicolaus Copernicus. The geocentric model, which placed Earth at the universe's center, couldn't easily account for what Galileo was seeing through his telescope. Picture Galileo on cool evenings, positioning his telescope, carefully sketching what he observed, noting positions and changes night after night. The patience required for these observations, waiting for clear skies, carefully mapping moon positions, tracking patterns over weeks and months, demonstrates his commitment to thorough documentation. The telescope's broader lesson, sometimes a new tool, technique, or perspective, reveals dimensions of reality previously invisible. The world contains layers we miss without appropriate instruments, whether physical instruments like telescopes or conceptual instruments like new frameworks for understanding. For centuries, the accepted cosmology placed Earth at the center of the universe. Sun, moon, planets, and stars all revolved around stationary Earth. This geocentric model matched direct observation. The sun obviously moves across the sky daily, and we feel no motion beneath our feet. The model also aligned with certain theological interpretations, emphasizing humanity's central importance in creation. It fit common-sense intuition. It had the weight of tradition, authority, and apparent observational evidence supporting it. In 1543, Nicholas Copernicus had proposed an alternative. Earth and other planets orbit the Sun. This heliocentric model simplified certain astronomical calculations and explained planetary motions more elegantly. But it seemed counterintuitive. If Earth is spinning and orbiting, why don't we feel it? Galileo's telescopic observations provided physical evidence for heliocentrism. Jupiter's moons proved not everything orbits Earth. Venus's phases matched predictions of the Sun-centered model. The sheer number of stars suggested a vastly larger universe, making Earth's central position less plausible. But openly supporting heliocentrism brought Galileo into dangerous territory. The Catholic Church engaged in counter-Reformation efforts to maintain doctrinal authority, viewed challenges to geocentrism as problematic. Certain biblical passages described Earth as stationary and the Sun as moving. Galileo believed scientific observation and religious faith could coexist harmoniously. God created both Scripture and nature. They couldn't truly contradict. Where they seemed to conflict, interpretation needed adjustment, either of Scripture or of observations, not denial of what could be directly seen. This position proved politically difficult. In 1616, church authorities declared heliocentrism contrary to Scripture. They instructed Galileo not to teach or defend it as fact. He could discuss it as a mathematical hypothesis for calculations, but not as physical reality. For years, Galileo largely avoided the controversial topic publicly. But in 1632, he published Dialogue Concerning the Two Chief World Systems, presenting arguments for both geocentric and heliocentric models through fictional dialogue between three characters. Though structured to appear balanced, the text clearly favored heliocentrism. The character defending geocentrism, named Simplicio, presented weak arguments that were systematically refuted. The pro-heliocentric arguments were compelling and backed by observational evidence. This brought formal charges. In 1633, at age 69, Galileo faced trial before the Roman Inquisition. Under threat of imprisonment or worse, he formally recanted his support for heliocentrism, stating he had erred in suggesting Earth moves. The trial became symbolic of broader tensions between free inquiry and institutional authority, between observation-based knowledge and tradition-based belief, between emerging scientific methods and established knowledge systems. Following his trial and forced recantation, Galileo spent his remaining years under house arrest. He couldn't travel freely, couldn't publish without approval, couldn't receive visitors without permission. For someone who had maintained correspondence with scholars across Europe, this was a severe restriction. Yet even confined, Galileo continued working. Unable to publish on astronomy or heliocentrism, he returned to earlier studies of motion, materials, and mathematical principles that had fascinated him before his telescopic discoveries. During this period he wrote discourses and mathematical demonstrations relating to two new sciences. This book summarized decades of works on motion and strength of materials. Published in the Netherlands beyond the Inquisition's reach, it became foundational for classical mechanics and engineering. The perseverance this required is worth noting. Galileo knew his astronomical observations were correct. Evidence clearly supported heliocentrism. Yet authorities demanded he deny it. He complied outwardly to preserve his life and ability to work, while maintaining his understanding internally. Some view this as pragmatic wisdom, protecting the ability to continue contributing by conceding symbolic battles. Others see it as regrettable capitulation to unjust authority. Perhaps it was both. Human responses to impossible situations rarely fit neat categories. His final years brought physical decline. He went blind, possibly from observing the sun through telescopes without adequate protection. His beloved daughter, Sister Maria Celeste, who had provided emotional support through his trials, died in 1634. He experienced aging's diminishments while cut off from the intellectual community he had helped create. Still, he maintained correspondence with supporters, received occasional visitors when permitted, and continued thinking about problems that had engaged him for decades. Even diminished and restricted, his mind kept working, questioning, seeking understanding. Picture Galileo, in those final years, blind, confined, grieving, yet still mentally active, unable to observe the stars he had revealed, but still thinking about motion, mathematics, and nature's patterns. The external circumstances were difficult, but the interior life of curiosity and understanding continued. He died in January 1642, still technically under house arrest. The church initially wouldn't allow burial with honors, though his remains were eventually moved to Florence's Santa Croce Basilica. The image of Galileo under house arrest, persecuted for observing nature carefully and reporting honestly what he saw, became a powerful symbol. It represented science's struggle for independence from religious or political authority, observation's priority over dogma, evidence's importance over tradition. Galileo's conviction that nature operates according to mathematical laws represented a profound shift in understanding reality. Before this mathematical approach became dominant, nature was often understood through qualities, purposes, and essences. Why things behave as they do, what they naturally seek to become. The Aristotelian approach asked qualitative questions and provided qualitative answers. Why do objects fall? Because the earth element seeks its natural place at the universe's center. This explanation has certain logic, but enables no precise predictions or measurements. Galileo's approach asked quantitative questions. How fast? In what proportion? According to what mathematical relationship? These questions proved extraordinarily powerful for understanding and predicting natural phenomena. Consider falling objects again. The mathematical description, distance proportional to time squared, allows precise calculation. If you know how far something falls in 1 second, you can calculate exactly how far it falls in any time period. Mathematics transforms description into prediction. This mathematical approach revealed deep universality. The same equation describing a ball rolling down a ramp applies to any uniformly accelerated motion anywhere. The same principles governing pendulum motion work, whether the pendulum is in Pisa or anywhere else. Mathematical laws showed consistency across time and space. This universality itself was profound. Natural laws work the same everywhere, for all objects, at all times. The universe isn't capricious or arbitrary, but lawful and comprehensible through systematic study. This regularity makes science possible. Galileo's focus on measurable properties, size, shape, position, motion, time, rather than qualities like color, taste, or smell, defined what science could address. Science studies what can be measured and mathematically describe. This establishes clear boundaries for scientific method. This doesn't make unmeasurable aspects of experience unreal or unimportant. Beauty, meaning, value, these matter profoundly. But they lie outside science's domain. Science addresses quantifiable patterns, not subjective experience or meaning as such. The mathematical approach also enabled technology. Once you understand how things work mathematically, you can engineer applications. Understanding projectile motion enables better artillery and architecture. Understanding pendulum motion enables accurate clocks. Mathematical knowledge translates into practical power. This connection between mathematics and nature continues driving modern science. Physics, chemistry, even biology increasingly rest on mathematical foundations. The approach Galileo pioneered has proven remarkably fruitful. The broader lesson, beneath apparent complexity, often lies simpler mathematical patterns. Finding these patterns requires patience, careful measurement, and mathematical thinking, but discovering them provides both deep understanding and practical capability. Galileo's life illustrates how scientific progress actually occurs, not through pure reason alone or random observation, but through systematic interaction between theory, observation, and experiment. He didn't observe without preconceptions. He had theoretical expectations based on mathematical reasoning, but he tested these expectations against careful observations. When observations contradicted expectations, he modified his theories. Then he tested the modified theories with new observations. This cycle of prediction, observation, refinement produced increasingly accurate understanding. Early ideas were rough. Repeated testing refined them. Eventually, the mathematical descriptions matched observations so precisely that confident predictions became possible. Galileo also recognized that good experiments require controlling irrelevant factors. When studying falling motion, air resistance complicates the pattern. Ideally, you'd eliminate it by creating a vacuum. Since he couldn't do that practically, he used inclined planes to slow motion and reduce air resistance's effects. This shows another key principle. When you can't observe something directly, find ways to study it indirectly while preserving essential features. Slow motion down with inclined planes. Use pendulums to study rhythm and timing. Thus, create conditions where patterns become visible. He also understood that single observations prove little. You need repeated trials under varying conditions. Patterns that appear consistently across many observations likely reflect genuine natural regularities rather than accidents or measurement errors. This systematic approach, form hypotheses, test through observation, refine based on results, repeat, became the foundation of scientific method. It's not purely logical reasoning, which can produce elegant but false theories, or pure observation, which can miss underlying patterns. It's disciplined interaction between thinking and looking. The method requires patience. Quick conclusions based on limited observation often prove wrong. Careful accumulation of evidence takes time, but this patience produces reliable knowledge that makes accurate prediction and practical application possible. Consider how this applies beyond formal science. When facing complex problems or important decisions, the same systematic approach helps. Observe carefully before acting. Test assumptions when possible. Refine understanding based on results. Stay open to revising initial ideas when evidence suggests they're incomplete or wrong. While Galileo emphasized observation and experiment, he also used imaginative reasoning, thought experiments, exploring situations impossible to create physically, but illuminating through logical analysis. Consider his famous thought experiment about falling objects. If heavier objects fall faster than lighter ones, as Aristotle claimed, what happens when you connect a heavy object to a light one? The light object should slow the heavy one down, since they're connected, but the combined object is heavier than either alone, so it should fall faster than the heavy object by itself. This creates a contradiction. The combined object should simultaneously fall slower and faster than the heavy object alone. This logical contradiction suggests the initial premise must be wrong. All objects, regardless of weight, fall at the same rate when air resistance is negligible. Galileo reached this conclusion partly through reasoning before fully testing it experimentally. He also imagined scenarios like motion on a perfectly smooth horizontal surface without friction. In reality, friction always exists, but imagining frictionless motion revealed that an object in horizontal motion would continue moving indefinitely without any force maintaining the motion. This insight contributed to what would become Newton's first law of motion. These thought experiments show that imagination and careful reasoning complement observation and experimentation. You can explore possibilities through logic, identify contradictions in accepted ideas, and develop theoretical frameworks that guide future observations. The mind itself becomes an instrument of discovery. Even without physical tools, you can see far into the implications of principles, explore consistency of different ideas, and develop frameworks for understanding observations. This balance between observation and imagination, between empirical testing and logical reasoning, characterizes mature scientific thinking. Neither alone suffices. Observation without a theoretical framework is mere description. Theory without observational testing is speculation. Together, they produce powerful understanding. The lesson extends beyond science. In any complex domain, business, relationships, personal development, both careful observation of what is and imaginative exploration of what could contribute to wisdom. Watch carefully, but also think creatively about possibilities, implications, and alternative framings. Galileo understood something important about knowledge. It's provisional and subject to refinement as observations accumulate and methods improve. His confidence came not from believing he'd reached the final truth, but from having a solid observational foundation for his claims. He didn't claim absolute certainty about everything. He claimed high confidence in carefully verified observations and the mathematical patterns describing them. Future observations might refine understanding, but basic patterns he documented would remain valid within their domain. This represents healthy epistemic humility. Scientific knowledge isn't absolute truth handed down from authority. It's better current understanding based on systematic observation, subject to revision if better evidence emerges. Confidence comes from careful testing, not from claiming infallibility. This attitude contrasts with dogmatic certainty that refuses to consider evidence contradicting established beliefs. Galileo faced authorities certain about geocentrism based on textual interpretation and tradition, unwilling to seriously consider observational evidence. The conflict wasn't between faith and science, but between different approaches to knowledge. Galileo believed truth comes ultimately from careful observation of God's creation, the book of nature, not solely from human interpretation of texts. Both scripture and nature came from God, so they couldn't truly contradict if properly understood. His position was that when observational evidence clearly contradicts literal textual interpretation, perhaps the interpretation needs reconsideration rather than denying what can be directly observed. The evidence from Venus's phases, Jupiter's moons, and lunar mountains was clear and verifiable by anyone with a telescope. This raises important questions about knowledge sources. How do we decide what to believe? Based on authority and tradition? Based on personal observation? Based on expert consensus? Some combination? In different domains, different sources appropriately carry different weight. For questions about physical nature, Galileo argued systematic observation should take precedence. For moral or spiritual questions, other sources of wisdom apply. Recognizing different domains and their appropriate methods avoids confusion. The broader lesson: hold beliefs with appropriate confidence based on their foundation. Strong observational evidence warrants confident belief. Speculation or inherited assumption warrants more tentativeness. Being clear about the basis for beliefs helps you engage evidence appropriately. While Galileo brought a rigorous mathematical approach to studying nature, he never lost sense of wonder at what he observed. Scientific understanding and aesthetic appreciation coexisted in his experience. His writings about astronomical observations convey genuine excitement. Discovering Jupiter's moons, seeing lunar mountains, observing countless stars in the Milky Way. These observations amazed him, even as he carefully measured and documented them. This combination of precise observation and appreciative wonder represents an ideal balance. Understanding how something works doesn't diminish its beauty or significance. In many ways, deeper understanding enhances appreciation by revealing unexpected patterns and connections. Consider the moon's surface. Before telescopic observation, it appeared as a smooth, luminous disk, beautiful but mysterious. Galileo's observations revealed mountains, craters, varied terrain, making it more comprehensible as a physical place. Did this diminish its beauty? Many would say it enhanced appreciation by adding dimension and texture. Similarly with Jupiter's moons, discovering they exist adds marvel rather than subtracting it. The universe becomes richer, more interesting, more worthy of wonder, precisely because systematic observation reveals unexpected complexity. This suggests that science and wonder aren't opposed but complementary. Careful study reveals patterns and relationships that can evoke even deeper appreciation than ignorance or vague mystery. The more you understand about nature's intricate workings, the more remarkable it becomes. Galileo's example shows you don't have to choose between rigorous analysis and appreciative wonder. You can bring both careful measurement and genuine amazement to observation. The disciplined scientist and the wonder-struck observer can coexist in the same person, looking through the same telescope. This balance offers guidance for approaching life generally. Bringing both analytical understanding and appreciative awareness to experience enriches both dimensions. Understanding patterns in relationships doesn't diminish their value. Comprehending psychological principles doesn't make human behavior less interesting. Knowledge and wonder enhance each other. Galileo's achievements didn't come from sudden inspiration or brief, intense effort. They emerged from sustained work over decades, building instruments, conducting experiments, making observations, performing calculations, refining understanding gradually through accumulated effort. Consider the telescope observations. These required clear nights, patient positioning of instruments, careful sketching of what he saw, repeated observations to track changes, meticulous record-keeping. Night after night, month after month, building a comprehensive picture through accumulated detail. Or the inclined plane experiments, rolling balls down ramps hundreds of times, measuring tiny increments, collecting water from timing clocks, calculating ratios, looking for patterns in numbers. Hours of repetitive work, producing data points that gradually revealed mathematical relationships. This persistence illustrates something important about mastery. Breakthroughs usually emerge from sustained practice rather than lucky accidents. The prepared mind recognizes significance in observations because it has built foundation through long engagement. Galileo's daily practice involved instrument building, observation, calculation, correspondence with other scholars, teaching, writing. Each activity contributed to developing skill, deepening understanding, and building the knowledge base that enabled major discoveries. This offers practical guidance. Significant achievement usually requires sustained effort over extended time. Quick results are appealing, but genuine mastery develops slowly through patient accumulation of skill and knowledge. Daily practice matters more. than occasional intense effort. The same principle applies to any craft or discipline. Musicians practice scales daily for years. Writers write regularly to develop voice and skill. Athletes train consistently. Consistent practice over time builds capabilities that occasional enthusiasm never produces. In intellectual work, daily engagement with ideas, regular reading and thinking, sustained attention to questions, these create conditions where insights emerge naturally. The breakthrough that seems sudden often has roots in years of preparation. Galileo died in 1642, but his influence extends across centuries. His observational discoveries, mathematical approach, experimental methods, and conviction that nature reveals truth through systematic study shaped the development of modern science. His astronomical observations sparked a paradigm shift in understanding Earth's place in the cosmos. Though he faced oppositions and consequences, the evidence he provided eventually convinced the scientific community that planets orbit the Sun, not Earth. His studies of motion laid the groundwork for classical mechanics. Newton, born the year Galileo died, built directly on Galileo's work when developing comprehensive laws of motion and gravitation. The connection between these two giants of physics is direct and acknowledged. His experimental method, combining observation, measurement, mathematics, and hypothesis testing, became the model for scientific inquiry. The approach he pioneered continues guiding how scientists investigate nature's workings. Beyond specific discoveries, Galileo demonstrated that careful observation could overturn long-accepted beliefs. He showed that systematic study of nature yields reliable knowledge. He proved that mathematics provides a powerful language for describing natural phenomena. His conflict with religious authorities became a symbol of science's relationship with institutional power. The story of Galileo's trial reminds each generation about the importance of allowing evidence-based inquiry, even when findings challenge established views. Modern astronomy, physics, and scientific methods all bear Galileo's influence. Every satellite observing the cosmos, every precision measurement of motion, every mathematical model of natural phenomena connects back to approaches he pioneered. His life also offers lessons beyond science: the courage to trust your own careful observations, the patience to accumulate evidence systematically, the intellectual honesty to report findings even when they contradict accepted wisdom, the persistence to continue working despite opposition. These qualities remain relevant whatever domain you engage in. What can we learn from Galileo's life and work centuries after his death? Several principles seem broadly applicable. Observation before assumption. Look carefully at what actually is before concluding based on what you expect or what others claim. Reality reveals itself to patient attention. Test beliefs against evidence. Don't cling to ideas that observations contradict. Being wrong and correcting course surpasses being certain and persistently wrong. Mathematics reveals patterns. Quantitative thinking often illuminates relationships that qualitative description obscures. Numbers provide precision and clarity. Tools extend perception. New instruments, whether telescopes or conceptual frameworks, reveal dimensions of reality previously invisible. Stay open to new ways of seeing. Systematic method beats casual observation. One-off observations prove little. Repeated measurements under varied conditions reveal reliable patterns. Persistence accumulates into achievement. Sustained daily effort over time produces results impossible through brief, intense bursts. Patient accumulation builds mastery. Wonder and rigor coexist. Careful analysis doesn't diminish appreciation. Understanding can deepen wonder at nature's intricate workings. Courage to question serves truth. When observation contradicts accepted wisdom, intellectual honesty may require standing against consensus. This takes courage, but serves understanding. Knowledge remains provisional. Confidence should match evidence quality. Stay open to refining understanding as better evidence emerges. These principles apply beyond formal science. In any domain requiring sound judgment, business, relationships, personal development, these approaches to knowledge and understanding prove valuable. As you settle toward sleep, consider Galileo's patient approach to understanding. He didn't demand instant answers or quick results. He watched carefully, measured repeatedly, thought deeply, refined gradually. Picture him on quiet evenings, positioning his telescope, sketching observations by candlelight, noting patterns in his journals. Each observation is a small contribution to accumulated understanding. Each measurement adds to the foundation of knowledge. Or imagine him in his workshop, rolling balls down inclined planes, measuring water from timing clocks, calculating ratios. Patient repetition, revealing mathematical relationships hidden in everyday motion. His life shows that understanding emerges from sustained attention, careful observation, and patient accumulation of evidence. No shortcuts, no sudden magic, just consistent engagement over time, producing deep comprehension. The universe revealed its patterns to him, not because he was specially gifted, but because he looked carefully and patiently. The same patterns are visible to anyone willing to observe, with similar care and dedication. As you drift toward sleep, let this sink in. Truth often hides in plain sight, waiting for patient attention to reveal it. The answers you seek may be visible now, requiring only the patience to look carefully and the humility to let reality teach you. Like Galileo, watching the stars drift slowly across the night sky, each point of light following its predictable path, you can approach your own questions,